So in this video, we are going to apply the identities that we have already gone over and in chapter 4 and use them to verify some new trig identities. All right, to do that, we need a quick recap, and hopefully you already have these memorized. You do have a formula sheet in your Canvas, the course information module, where you can print out all trig identities that you do need to memorize. These will not be on a formula sheet. And these are our pretty basic ones. So we start with our reciprocal identities. So I listed all 6 trig functions. You see it in front of you, and what they are equal to. So sine alpha equals 1 over cosecant alpha, and cosecant alpha equals 1 over sine alpha. Then I also have the quotient identities across from that. You have tan alpha equals sine over cosine, and cotan alpha equals cosine over sine. I want to stop there for 1 second and talk about where the reciprocal and quotient identities are kind of important, because as we go through the set of examples that I'm going to do in this video, one of the first, I'm going to give you kind of little hints along the way, like, hey, you can try this, and if this doesn't work, then try this. And the first thing you're going to try, or the first kind of way that you can solve these, is to turn everything into sines and cosines. And if you think about it, all 4 of the other trig functions can be written as a sine or cosine. So for example, cosecant alpha is 1 over sine. Secant alpha is 1 over cosine. Tangent alpha is sine over cosine, and cotangent is cosine over sine. So kind of one of the guidelines and one of the things you can try when verifying an identity is just to turn things into sine and cosine, and you would use these particular identities for that. The other thing is to understand your Pythagoreans. So listed, you have the 3 at the bottom of the screen. You have the 3 Pythagorean identity. Sine squared plus cosine squared equals 1. This is a nice one because when you see sine squared plus cosine squared on the same side of a trig identity, you can just cross them out and make them equal 1. If you have a 1 plus tan squared equals secant squared. And also, don't forget the variations of these identities. And what do I mean by that? Well, where you have 1 plus tan squared equals secant squared, you also have the identity of secant squared minus tan squared equals 1. So just kind of keep that in mind, that you may need to use variations of some of these trig identities. For example, you might have to replace a sine squared with 1 minus cosine squared. You can do that because these are 3 proven identities, meaning they are true equations. And since they're true equations, you can now manipulate them using the additive inverse property and say subtracting cosine squared from both sides to get sine squared equals 1 minus cosine squared. All right, so you can do that on these. All right, let's take a look further. I also listed, this comes up once in a while if you see an odd thing like cosine of negative alpha. You can apply your even odd and just make a quick little statement next to it that says, hey, cosine's an even function. So I'm going to replace cosine. You don't have to say the rest, but you can then replace cosine of negative alpha with just cosine of alpha. You can replace sine of negative alpha with negative sine alpha. But next to that, you're going to make the statement because sine is an odd function. And of course, if you use any of the identities above, notice I gave you some shortcuts. Instead of writing out, I used the reciprocal identity. I said RI, QI, PI for reciprocal identity, quotient identity, and Pythagorean identity. Okay. So what I'm going to do for the examples in this, I'm not going to go over the exact examples that are in your textbook because I want you to have a whole other set that you can kind of use as a guide. But these are listed, they're just not worked out for you in the book, so I'm going to use those examples, the checkpoint examples. All right, so the first one is I want to verify the identity, and these will be the directions to all of them, so I'm not going to keep writing those directions. So the first one I want to do is cosine of x times cotan of x plus sine of x. I want to verify that all of that equals cosecant of x. All right, so I'm going to do it here just for fun. I'm going to draw that line. Remember, sorry, can never move one over to the other side. And as you can see, cosecant already is pretty darn simplified. So we're going to keep our right-hand side as just cosecant x. And you will find along the way, sometimes it is useful to manipulate both sides individually until they equal each other. Sometimes it's useful just to manipulate one to look like the other. In this case, we're going to manipulate our left-hand side to look like our right-hand side. So this falls under the category of if you see a bunch of, notice how we have a cosine, we have a sine, but then I have a cotan. One of the things I can do is change, so I'll put like little notes on the side here. Change your trig functions to all cosine sine. And you can apply that to both the left or right. There's a lot of different options. I'm not going to go through every way to solve an identity. I will show you one way and maybe talk about other ways it could have been done. All right, so cosine, well, that's already a cosine. I don't need to do anything. I can keep that as cosine x. Cotangent, if you look at your quotient identities, is equal to cosine x over sine x. And you can put a little note to the side. I used a quotient identity. Cotan equals cosine over sine. You've got to put some justification for what you did. I'm not going to change sine x because sine x is already a sine. So what I'm doing is moving everything into sines and cosines. I can even do it over here if I wish. I can, because I'm not manipulating and moving things from one side to the other, I can change cosecant to 1 over sine x. All right, and you'll see later on it really doesn't matter if you do that or not because you can apply something to the other side. But let's continue. All right, cosine times cosine, of course, is cosine squared x over. You do not need to justify when you just use a basic algebraic property. Okay, so I multiplied 2 cosines together. I don't need to justify that. Now, here's what I want you to notice. Whether you leave this as cosecant x, the right-hand side, or change the right-hand side to 1 over sine x, it's a single term. I want you to look at that left-hand side. That left-hand side has 2 terms. So let's see, this is the left-hand side is term 1, term 2. The right-hand side only has 1 term. When you see stuff like that, another idea, of course, is to get the 2 terms into 1 term. In other words, the left-hand side, I have cosine squared over sine plus sine. I can get a common denominator and bring them together as 1 fraction. You are going to do this often, so let's talk about that common denominator. Well, my first term, term number 1, has a denominator of sine. Term number 2, as you can see, does not have a denominator. Technically, that is over 1. So to get a common denominator, and I'll put it in red, I would need to multiply the sine x by sine x over sine x to get them to be the same. So what does that look like when I make that multiplication? I now have my common denominator, so I can put it as one fraction. Keeping in mind what we have posted on the other side, because we did change cosecant to 1 over sine. Do you see it? Cosine squared plus sine squared, we know, equals 1 by Pythagorean identity. Cosine squared plus sine squared equals 1. So make that 1 over sine x equals 1 over sine x. Done. Now, had I kept, I do want to point this out. Had I kept the right-hand side to be 1 over cosecant x, it would look like this. You can't check that off yet. You would still need, and I don't care whether you change 1 over sine x to cosecant x or cosecant to 1 over sine. You still need to manipulate either the left-hand side or the right-hand side. You could do this. It is not until they are exactly equal that you can do your check mark. Okay? And what did I use? I used a reciprocal identity here. Okay? So be careful. Even up here, when I used reciprocal identity, I did need to make a note that said I used reciprocal identity. Right there. Okay? This isn't about getting the final answer. I know that's hard to imagine. This is about, did you apply the proper steps in between? Okay, so yeah, you're not going to be able to easily look this one up on AI. And you got to be careful, because when you do that, AI could use more advanced techniques that are in this course or that you have learned. So yeah, just study your identities, know your identities, and apply them properly. Okay? All right, let's just continue doing examples now so you can see a bunch of different ways. Example 2. And again, there's a whole other set of examples in 5.1 of your digital textbook that you can get through My Math Lab. So the one I'm going to do here is 1 plus cosine alpha over sine alpha Nope, that's not the one I want to do next. Well, that's okay. We'll do this one next. No problem. It follows very similar to the one we just completed in that notice the left-hand side is essentially one big term. But my right-hand side here is 2 terms. So you have some choices to make here. Trying to bring 2 terms on the right-hand side into 1 term, or trying to take 1 term and split them into 2. And that's what we're going to do here. We're going to look at the 1 term on the left-hand side and see if we can split it into 2 terms. Now, what allows us to split? Because while sometimes it's easier to bring terms together with a common denominator, other times it might be easier to separate. So what I want to do here is separate. Let's try it and let's see what happens. 1 and cosine theta are over this common denominator sine theta. When I break it up, it looks like this. It looks like like 1 over sine theta plus cosine theta over sine theta. And I'm going to keep the right-hand side exactly the same for now. All right, well, what do I know about, and again, you always have options. If you want to, you can go to the right-hand side and turn everything into sines and cosines. Or you can go to the left-hand side and turn them into not cosines and sines. You have different methods of going about doing this. So you might recognize, oh, wait a minute, 1 over sine is cosecant because of a reciprocal identity, right? Cosine over sine is cotangent because of a Pythagorean identity. Notice I put the identities I used. Oh, I didn't have to do anything to my right-hand side. Right-hand side stayed cosecant theta plus cotan theta. They equal each other. So let's move on. All right, number 3. So when we talk about different methods to use, changing things to sines and cosines, bringing two fractional terms together as one with a common denominator, taking one term that has a single denominator and breaking it up into 2 fractions. So these are all just methods to try. What you do is based, it has to go by what the problem looks like. Okay, next one. Let's do sine x. Whoops, I want minus, not plus. Sine x minus sine x cosine squared x equals sine cubed x. All right, so as you can imagine, my left-hand side is way more complicated than my right-hand side, so we're going to leave that right-hand side alone, and we're going to work with the left-hand side. Notice these 2 terms. I have term 1, again. Oops. And this whole thing is term 2. They have something in common. When terms have something in common, you can factor. So another kind of method to try is factoring, if possible. In this case, they both have a sine x, so I can factor out sine x. When I factor out sine x of the first term, I'm left with just 1. Cosine squared x. So you remember, and all I did was factor. You remember I talked about the Pythagorean identities and how you have to know the variations. So let me flip up to the Pythagorean identities again. There they are. And I'm highlighting sine squared plus cosine squared equals 1. Well, remember my problem had 1 minus cosine squared. Apologize again for the dogs barking. So, if I do 1 minus cosine squared, wouldn't that indeed equal sine squared? So let's come back down to my problem. And off to the side, I'm going to make a note. Pythagorean identity. We know that sine squared plus cosine squared equals 1. So sine squared has to equal 1 minus cosine squared. So I have my sine x times, I'm going to replace this. Now, here's where you got to be careful. You are not done. They're not identical yet. I know in your head you're going, yes, they're equal. That's not the point of verifying. You have to finish it off with the algebraic step of multiplying sine times sine squared. When you multiply sine times sine squared, you get sine cubed x equals sine cubed x. This is not where you want to attempt to take shortcuts. You will lose valuable points. And it is verified. So factoring is kind of another tool that comes up often. This next one is a little bit more complicated in that you may not recognize to do it. So it's an important one to see. So you can kind of identify, ooh, I might need to do that sometimes. So what is that? All right, let's give the problem cosine x for 1 plus sine x is 1 minus sine x over cosine x. Okay, so I got my left-hand side and my right-hand side. So when it's one term equals one term, and one is neither more complicated or less complicated than the other. So you might be thinking, I don't even know where to begin here. Looking at that left-hand side, cosine over 1 plus sine x, they have a single numerator and two terms. You can't even split that one up. It doesn't work. You can attempt to split the right-hand side up, and here's the thing that often happens. You might start to do things and realize they're not getting you anywhere. So sure, I could take 1 over cosine x minus sine x over cosine x. And you might start saying, well, okay, I split it up. Well, I know 1 over cosine is secant x, and that is tan x. And then you're looking at your left-hand side and say, well, that does not even, that looks further away from what my left-hand side of cosine x over 1 plus sine x is than my original problem. And if that happens, then you go, all right, let me start over. I'm not getting anywhere by attempting that. And that is what is going to happen when you go to solve these, verify these trig identities. So here's another little trick. When you're stuck, this trick kind of comes into play when you have a denominator on either the left or right hand side that looks something like, oh, I don't know, 1 plus sine x, maybe 1 minus sine x, 1 plus cosine x, 1 minus cosine x. If you have denominators that look like that, then we can multiply by something we call, you've worked with it before, you've worked with it with radicals. It doesn't only apply to radicals. You're going to work with it in your calculus classes. Conjugate. Conjugates are these kind of cool things because when you multiply a binomial, meaning two terms, by its conjugate, you get this nice little binomial with the terms squared. So for example, what is a conjugate? Let's stop there for a second. The conjugate of x minus 3 is x plus 3. The conjugate of x plus 5 is x minus 5. It's the identical binomial. You're only going to multiply binomials by conjugates with the second term, the sign changed. Why are they so useful? Well, let's multiply x minus 3 times x plus 3. X times x is x squared. Notice, if I were to FOIL this out, I'd get minus 3x plus 3x. They cancel away, right? And then I get minus 9. They cancel. So it's just x squared minus 9. X squared minus 9. Same idea here. X squared minus 25, because 5x minus 5x is going to cancel away. And you still may be thinking, well, I don't know how that helps me here. Let's try it, and hopefully you will see why it helps you. All right. you have to multiply the entire fraction. So the conjugate of 1 plus sine x is 1 minus sine x. And you cannot multiply just the denominator by 1 minus sine x because you're changing the value of the left-hand side. But I can, if I multiply the numerator as well, all I really did is multiply by the number 1, and we know that does not change the value. Okay. Well, let's work it out and see what happens. So I can multiply this out, but I'm going to say sometimes let's not distribute yet. You'll see in a second. Let's just leave it as cosine x times 1 minus sine x. So, knowing our middle terms are going to cancel, it's 1 times 1. Now watch. I would get negative sine x plus sine x. They're going to cancel away. So I'm going to be minus sine squared x. All right, let's stop and think about what we did so far. We multiplied by conjugate. All right, did the multiplication here. I did not distribute the numerator. Again, you'll see why in a second. Well, what is 1 minus sine squared x? Remember what I said. Let's go back up to the top. Well, let's go to the previous problem. That'll help you. 1 minus cosine squared was sine squared because of the Pythagorean identity. So 1 minus sine squared must be, apply the Pythagorean identity to the numerator, to the denominator, sorry. Keep the numerator exactly as it is. Notice I haven't even touched the right-hand side, so we'll worry about that in a minute. Oh, cancel away. Cosine x takes away one of those cosine x's. I got 2 of them though, so I'm left with 1 minus sine x. That's why I didn't distribute, because I knew I could see it was going to cancel. Hey, what was that right-hand side again? Yeah, look at that. 1 minus sine x over cosine x. Done. So this is one of those tricks, the conjugate trick, that, not a trick, but it becomes useful. You just kind of have to recognize when I might use that. And this is kind of a good recognition. If you have a denominator with one of those terms and nothing else was working for you, that would be a nice way to go, is to try that. Okay. Again, I know this is we're at 30 minutes, but I want to go a little further and do about 3 more problems. What number was that? That was 4. Because then you can scroll through the video till you get to the examples you want to see. Let's do here. Secant x plus cosecant of negative x over secant x times cosecant of x equals sine x minus cosine x. All right, a couple things I want to notice about the left-hand side and right-hand side here. Well, my right-hand side is just sines and cosines. My left-hand side has a lot of stuff going on. So you might question, even though it's going to look a little complicated, there's nothing we can do to sine x minus cosine x. I mean, we could change them into cosecant and secant, and you can try to bring them together, or we can change our secants and cosecants and the sines and cosines. There's always more than one way. The first thing I would say is, let's get rid of that negative x. Don't like the negative x. All right, so you got to ask yourself, is cosecant an even or odd function? Well, cosecant is the reciprocal of sine. Sine is an odd function. So it becomes plus negative cosecant x and I don't want to write plus negative, right? Let's make that minus cosecant x. So there's two different methods of really going about this problem. I'm going to go through what I might consider the longer method and kind of give you a hint to try another method. Only because it does go over some concepts you might have forgotten. So maybe you don't know what to do and you just want to change everything to sine and cosine. So, well, if you do that, secant, of course, is 1 over cosine x. Cosecant is 1 over sine x. Secant is, so that's 1 over cosine x. You get this kind of messy complex fraction. And again, I'll challenge you to try it another way when we're done. But I did want to review the complex fraction. Because you might come across problems that have this complex fraction in it, and you have to say to yourself, oh, how do I get rid of complex fractions? Well, I find the easiest way is to remove all of the cosine, sine, and cosine times sine. All right? All of the denominators by multiplying by the common denominator. So that's just the first one is just cosine. The second term in the numerator is just a sine, but the denominator is cosine times sine. So if I multiply cosine x, sine x, every term by cosine x, won't I eliminate all those denominators? Cosine x, sine x. So when I multiply it, cosine x, sine x, we'll look at the denominator first because the denominator is kind of easy. It cancels away and it just becomes a 1. When I take this numerator of cosine x, sine x, and distribute it into the numerator of our complex fraction, well, in the first term, the cosines are going to cancel, and I'm left with sine x. And in the second term, the sines are going to cancel, and I'm left with cosine x. And you're essentially done. Because our right-hand side was indeed sine x minus cosine x. So you changed using our reciprocal identities. Think back of what we did. Simplified a complex fraction. And you got your numerator. You got your right-hand side. Now, the other option might be to change right-hand side to 1 over cosecant x minus 1 over sine x. Or not sine x, sorry. Secant x. using reciprocal identities, and bring those two fractions together to make it look like the left-hand side. So you have different options with that particular problem. Okay? Let's take a look at this will actually be the last one I do, number 6. Number 6, I believe, is one of those where it's easier to kind of work with both sides. So let's give it a try. Okay, the identity is 1 over 1 plus sine alpha plus 1 over 1 minus sine alpha equals 2 plus 2 tan squared alpha. Now, actually it was theta. I know I was calling it alpha. It doesn't matter. Theta, alpha, use whatever angle you want. That's neither here nor there, but I was saying alpha and I wrote theta. Okay. So there's a lot going on, but you may be looking at, hopefully at this point you're going, ooh, see that left-hand side, how there are two terms, 1 over 1 plus sine theta plus 1 over 1 minus sine theta. What if I brought those together? What might that look like? Now, it's not going to be easy because one denominator is 1 plus sine theta and the other denominator is 1 minus sine theta. That means I literally have to, let's see here. I'm going to rewrite it, but give it more space. I'll do it in red. My common denominator, of course, is 1 plus sine theta times 1 minus sine theta. So this first one needs a 1 minus sine theta. First part of the fraction. The second term on the left-hand side needs a 1 plus sine theta. And right now I'm not doing anything. I'm just leaving to the right-hand side, leaving that alone. Okay, let's bring them together. It's going to give me 1 minus sine theta plus 1 plus sine theta, all in the numerator, over that common denominator of 1 plus sine theta times 1 minus sine theta. Okay, I'm gonna put this together. I'm going to simplify this. All right, I'm going to simplify this. 1 minus sine theta plus 1 plus sine theta is 2, I believe, correct? Just 2. Because our sine theta and minus sine theta is going to cancel away. And the denominator, I'm multiplying conjugates together again, so it's 1 minus sine squared theta, because I know they're conjugates. And you're like, how is that even going to start to look like my other side? Well, maybe, because again, I brought these two together as one fraction. Before I even do anything else, I know there's more I can attempt over here. You know, we get 2 over cosine squared, but before we go there, let's start taking a look at the other side. Well, I think the obvious choice at first is a chain tan squared into sine squared over cosine squared. And that was a quotient identity. And then I can get a common denominator. So this denominator of cosine squared theta that I just highlighted in yellow needs to be brought to the 2, so it's 2 times cosine squared theta over cosine squared theta plus 2 times sine squared theta over cosine squared theta. And I can, well, I can bring those together. I get 2 cosine squared theta plus 2 sine squared theta over cosine squared theta. And you may recognize, oh wait, that cosine plus sine is the Pythagorean identity, but before I can apply the Pythagorean identity, you need to factor out the 2. And yes, this is a long one, and you do need to show all the steps. Almost, you can start to see where they're coming together. Cosine squared theta plus sine squared theta equals 1. So that's 2 over cosine squared theta. I have 2 over 1 minus, well, okay, go back to your left-hand side and say, well, wait a minute. That is cosine squared theta by the Pythagorean identity. Boom, done. So here's an example of where we did work with both sides of that identity to get it verified. So again, you have a list of examples also in your textbook, section 5.1. It's around page 624, I think it starts. Nope, 622, actually 622. There's a list of examples that are good examples for you to try on your own, because then you can look at the textbook to see the steps. And we will be verifying more identities as we learn more identities to utilize and rules that we can use.